about asteroidal sat. This presentation's about what needs to be gone through to establish that an occultation event is can be justifiably claimed to be a the satellite of an asteroid. Now, we're just getting a bit sidetracked here. Okay. As I said earlier, we have 3 documented, well, there's actually now 4 asteroidal satellite discoveries published in the seabeds. There's another 2 on their way. And in the process of going through the issues with deciding that something is or is not a satellite, the process is not straightforward. Some people are expecting it to be a very simple tick a box answer, very straightforward. Well, it isn't. And I'm going to go through what's involved and go through the various events that have occurred. The critical event issue associated with what we do with these events has a basis tied up in history. In the early days of occultations, asteroidal occultations, yes, the primary objective was to measure the diameter and shape of asteroids, because back in the late 60s, early 70s, early 80s, they were a big unknown. In between 1977 and 1982, there were 5 instances where observers reported a secondary occultation, which was interpreted as being a satellite. Those observations were, almost all of them were visual observations, which means there's all the issues associated with the reliability of visual observations, particularly when you're staring down a telescope for several minutes, waiting for the occultation to occur, and all the issues associated with trying to keep focus on that period of time. Because back then, occultation predictions were not particularly accurate. You might have a path predicted to go over Sydney or Brisbane, and the real path might have gone over Russia, for example. The uncertainties were huge. Anyway, the real problem was there were 5 claims to satellites. At the time, that was concept of asteroids having satellites was almost heresy. But at some point they decided, well, we need to deal with this, and they undertook investigations with large telescopes, and the Hubble Space Telescope got involved. Serious money tied up in doing this, and no satellites were detected. And that's a serious problem. If they detected even one satellite, things would have been different. But they found nothing. And the consequence of that was reinforcing the common attitude then, or the common belief then, that asteroids don't have satellites. And hey, these occultation observers, when they report a satellite, well, clearly you can't believe them. And that followed on for the next 40-odd years. Huge levels of skepticism about any asserted discovery of a satellite via the occultation technique. Very damaging for us. Changes started in 2021 when Dave Galt and Dave Galt and Peter Nosworthy did a occultation of Arecibo, where they both got 2 events. They're separated by a distance and they both got 2 events. So prima facie, very good evidence for an occultation, for a satellite. The various criteria, well, the main criteria is associated with double stars and readily established that it could not be explained by a double star. In that process, we drafted a CBET, the official announcement thing, and put it through various people for review. And we had some professional people saying the certainty wasn't good enough. You can't rely upon the stuff. It could be a plane or a bird or whatever, somehow covering both observers. Basically, a straight-out denial of the fact of a satellite. But a month or 2 after that, there was another occultation by Arecibo, observed by 2 observers in America, and they both recorded 2 chords, and it provided excellent confirmation that it had to be a satellite. And a CBET was subsequently published. And then 9-12 months later, in the context of the Gaia project, a key researcher in Gaia, Paolo Tanga, investigated the asteroid data measurements in Gaia and found that the motion of the asteroid had a wobble in it. And he was able to, determine a period and a few other things. And most of the elements of the orbit of the satellite was determined. Curiously, whilst that is the case, so you've got effectively a very well-established fact that it was there's a satellite, there's an asteroid which has a satellite. In the International Astronomical Union's current way of identifying objects, they have preliminary designations and, if you like, final designations. Because of history and because of the nature of satellite discoveries by photometric techniques, a provisional designation of a satellite is currently not allocated unless there is a visual detection of the satellite. In other words, you've got to get an image through a bloody big telescope showing the satellite, or have a spacecraft go and visit the system. Otherwise, it's a discovery with no formal designation. I'm hoping that that's going to get changed within the next few years. Anyway, subsequent to that, we've had another 5 discoveries. Two of those are still to be formally announced. And I'm believing that the historical skepticism is waning, because we've now got, an established record of unarguable satellites. Now, given this history, we can't afford to make a claim to the discovery of a satellite without there being adequate justification. Apart from scientific rigor, the credibility of what we do really is highly dependent on us being able to demonstrate with a very high level of certainty that the satellite exists. And that means that we have a pretty rigorous review process, a process where occasionally we get a bit of pushback from people about why you're asking this and so forth. which is unfortunate, but it's history dictates we need to do it. So what am I up to? Is there a simple test for the discovery of an asteroid or satellite? Simple answer is no, there isn't. Satellites typically will be detected with observer recording 2 occultation events, which can also occur with double stars, or you can have occultation events observed by 2 observers, each one only getting a single occultation event, but when you combine them together, it's clear that you can only get the 2 separate events if the asteroid had a satellite. So the methodology is to exclude every other plausible explanation for the event. Range of possible explanations. You've got to go through and consider all possible explanations and make sure that you don't have that explanation available as well as the satellite. A critical issue, and it's caused some grief for a small number of people, is that possible explanations can vary from one event to the next. There is no magic bullet for you go through these simple steps and you do that exactly the same for each event. It's not that at all. You've got to have regard to all the circumstances of the event, which are all going to be different for every instance, and consider all possible explanations, exclude them. And in that context, while I've covered a range of issues in this presentation, those should not be considered to be complete considerations. It is quite likely there will be events in the future where other considerations will surface. The first issue, and this is possibly a dominant issue, is a double star. It's an issue which arises with every detection of a possible satellite. A key thing with a satellite occultation is that both the main body and the satellite will completely occult the star, which means that the light curve drop for both will necessarily be the same if it's a single star. If it's a double star involved, you could have just a single asteroid, single body occult for 2 components. Now, one issue there is if the components have a different magnitude, then the light drop will be different, assuming the light drop isn't so great as to go into the background noise. So if you have 2 occultation events and they drop to different light levels, it's not a satellite discovery, it's a double star. That is about the simplest issue to deal with. But that's not the end of it. Just because the light drops are the same doesn't mean that it's not a double star. If the components of the double star are very similar in brightness, when you put the 2 components together, the total magnitude is 0.75 magnitudes brighter than the individual. So if you have 2 light drops which are very similar, well, are the same, one of the things you need to establish is that the light drops of both are deeper than 0.75 of magnitude. If it's not deeper than 0.75 of magnitude, then you can't exclude the double star explanation. Now, 0.75 is the mathematical number. Given the type of accuracy we get with our light curves, the practical value needs to be a drop of at least 1.0 magnitudes needs to be evident. So you can be confident that the light drop is inconsistent with a double star of equal brightness. A corollary to this is if your recording does not go down to at least 1 magnitude fainter than the target star, you will be unable to claim any blips in the recording as being due to a satellite. So where you have make recordings where the target star is only just visible, satellite discoveries are out of the question. Something to think about when you're setting your camera exposures to do an event. Now, it's not as simple as does it drop 0.75 or 1.0 magnitudes, because it may be that the star disappears into the background, just disappears. Say if you've got a predicted magnitude drop of 8 magnitudes of a 12th magnitude star, no one's going to be able to record the bottom of the light curve. So what do you need to do then? You need to establish what the limiting magnitude of the recording is. That is, what are the faintest stars that can be consistently, reliably detected in the recording. And a critical thing here is you might think that, hey, with the light curve generated by Tangra, Pi movie, Peyote, Lie movie, it does start background subtraction. All you got to do is to measure the light level above the 0 point. No, don't rely upon that. It's unreliable because you need to calibrate the image against magnitudes, which may not be a linear issue in there. You just got to go through a process of establishing what the limiting magnitude of the recording is, and then showing that the stars, either that is more than 1 magnitude fainter than the target star, and that the starlight disappears entirely into the background. To do that, you need to visually inspect the recording to find the faintest stars that are consistently visible and identify them. Occult star mapping feature enables that to happen. You can overlay the semi-transparent map over your video recording, match the stars, and then click on the star, and you'll get the magnitudes of any star on the map, which are complete to magnitude 16. You also have an issue of color response of cameras, because our cameras are broad spectrum response, and then you might say they're blue sensitive or red sensitive, but the spectral response is quite broad. So in identifying limiting magnitude stars, you need to make sure that they're of a similar color to the target star. Now, in saying a similar color, that's where the magnitude differences between B and V or V and R are similar between the target star and any of the comparison stars you're considering and looking at. I think one of the things here in terms of establishing that the depth of the light curve is goes sufficiently far is if you can identify a star which is sufficiently bright to be reliably measurable with Tangra or Pi movie, then record that star as a comparison star with its known magnitude. And ideally, well, you need to have the light curve from the occultation event dropping below the light curve of the comparison star. And that gives you a very clear evidence, indication that the magnitude drop is deep enough. Final bit on double stars is, given the propensity of some people to look at stars with small magnitude drops, if the magnitude drop is less than about 2, you need to factor in the brightness of the asteroid. And the smaller the magnitude drop, the less likely it is you'll be able to detect a satellite. If you went for an event with a magnitude drop of 0.5, would you be able to detect a satellite in that occultation? I think you'd be pushing it. The data would be too noisy to allow any meaningful assessment of the light curve. Next factor, and it comes up on a semi-regular basis. Could the light curves be explained by a grazing occultation? Now, the issues there to consider is if you have two segments in a single light curve, disappearance, reappearance, disappearance, reappearance, what is the distance from the first disappearance to the final reappearance? How does that compare to the diameter of the asteroid? If it's vastly greater, then it's unlikely to be a grazing occultation. If it's rather smaller than that diameter, then it's hard to justify a satellite. If it's a bit larger, question is, could the asteroid have a significant apparent ellipticity? Think of asteroids like Eros or Cleopatra, the dog-boned asteroid, so that you've got a long asteroid with a bit of a bend in it or knobs at each end or whatever, with the two occultations being caused by things at each end of the asteroid. The issues you need to go through with this is if you've got a large ellipticity or blatantness of any such a body to fit the light curve chords, is that ellipticity compatible with known light curve brightness variations of the asteroid? In occult, we have access to the light curve variations, which are maintained for the minor, I forget the name of the database, but it's have immediate access to the maximum light curve variation for a huge number of asteroids. If the light curve variation is not much, but you need a very elongate asteroid to explain the occultations of greys, then that light curve is indication that it's not a graze. It can't be explained by an elongate asteroid because the evidence of it being elongate doesn't exist. It's contrary evidence. On the other hand, if the asteroid does have large light curve variation, it does elevate the issue of a graze to being a serious consideration. Similarly, is there a Dammit shape model, and does it indicate some required ellipticity? That gets a little bit complicated because the shape model could well be affected by the presence of a satellite. So it may indicate an ellipticity and be suitably elongated, but that's because of the existence of the satellite rather than inherent model. And one of the ones we've had, the Dammit shape model does suggest an elongate asteroid, but not so elongate as to be able to cause a grazing occultation. Similarly, with some of these, we've gone to the people behind the NEOWISE mission to see if their data indicates light curve variations to support ellipticity of the body. Another issue, and Dave Galt and Peter Nosworthy have had direct experience with this, but they're not alone. They each observed an occultation by an asteroid. The asteroid's diameter was less than the distance between the observers. How come they both got long occultation chords? The issues to be considered there is if you're going to put a single body to match the two observations, can you come up with a single body with a plausible shape having a total diameter which is broadly consistent with or compatible with the diameters from NEOWISE, Akari AQA, or the IRIS diameters? In other words, consistent with the general satellite determination of asteroid diameters. If you have to come up with the only way to explain it by a single asteroid is a very elongate, very large asteroid, well, that's not going to happen. Similarly, if you've got that large ellipticity, is it compatible with the known light curve variations, Dammit shape model issues, anything in the raw NEOWISE data to establish that? So that's a broad overview of the type of issues which to consider. And for each event, the key factors that are relevant to the event are different. I can assure you of that. There is no one single factor which determines the results of anything. And the amount of emphasis you got to put on one or another varies. Some things don't arise at all for an event, and other ones it becomes critical. So looking at the 5 events we have, this is the first event, first formal occultation discovery. The top one here, there's the 2 light curves for it, very short duration events. Here's a plot of the chords. First thing to note, the light curve drops for both occultation events, but it's to the same level. When you do the mathematics, the light curve drop is much more than 0.75 of magnitude. Forget how deep it was, but it's a very deep drop. So that excludes the double star stuff. Grazing occultation is sort of unlikely, but when you look at it on this object here, the main body, the upper chord is longer than the lower chord, which suggests that body has to be on that side of those chords. And on this one, that chord there is much shorter than that chord there, which indicates that this body has to be on this side of the chords, the observations. So you can't join a body between those chords. So those two chords exclude the possibility of a grazing occultation. Light curve drops are adequate, and it all looks good. Now, when the CBET was being drafted for that, huge resistance to the existence of being a satellite. Fortunately, that's 3 weeks later, two Americans, Kirk Bender and Richard Northenius, they recorded occultations by the same asteroid. That's their light curves. That's their chords. The nature of those chords. Any Gray's explanation totally out the window. Magnitude drops aren't so great, so not so clear cut there, but it's all consistent with that. So that's that was sufficient to get a CBET out and get our first formal acknowledgement of an asteroidal occultation discovery of a satellite. And as I said, subsequently, by investigating Gaia data, they established an orbital period, and orbital period, the diameter of the axis, which should be kilometers. You can get it from the fit to the occultation observations. The orbital inclination gets out of it. Basically all the parameters of an orbit. Yet no provisional designation allocated to the asteroid. It sucks. Dave and Peter, they like gaining fame for themselves, I think, because about 12 months later, they had another discovery. And this is the one I was referring to before. Here's their two light curves. They both get an occultation. It's a deep occultation. Both goes down to basically the background level. When you do the maths on the light curve and the drop, both well greater than the 1 magnitude type test. But when you plot the two chords, well, the asteroid diameter was much less than the distance between them. And yeah, the chords are just so far apart, both in time and whatever. To draw an ellipse to fit those two chords, be so elliptic. I mean, nothing like Cleopatra or Eros would go anywhere near that. So it could not possibly be explained by an elongated ellipse. And so that got explained or sent out as a CBET. There was a little bit of a slight qualification on the discovery, because there was, I forget the exact issue there, there was a minor element of reservation, but very minor. But that's been formally announced. Totally different considerations to the first, because two individual chords, no observer recorded both two chords. This is the third announced asteroidal satellite. First event, 3 light curves, 3 chords, 3 light curves. The top one is discovery, well, the observation by Jan Manek. A main drop with a short drop afterwards. The short drop is to the same light level as the main. Short light drop is greater than 1 magnitude, much greater. It's very hard to imagine a suitably shaped asteroid which could explain that very long curve and then somehow come out here with some sort of knob to to justify that second event. And the light curve data none of the light curves or shape model stuff gave any support for that. But a very short event, how confident are we being a real event? Well, again here, 3 weeks afterwards, which it's only a bit over 2 weeks afterwards, another occultation event by that asteroid with another detection, short event, same light curve drop, noisier light curve, but clearly that's consistent with a satellite. Its light curve drops is not to the full light to zero light level, but that's because the predicted light drop wasn't to a large light drop. So same light level, a positive indication that it's not a double star. Combine the two together, no doubt that's a satellite. And that's been published. It was published earlier this year. Now, this is an interesting one. Only one observation, occultation, and well, this is the light curve, single observer. 2 very well-defined events, short gap between them. What are the things to consider? Well, the length of the chords and the separation of the chords, far too great for any plausible elongate shape models. So on the face of it, a likely satellite discovery. Now, the observer for this event also happens to be involved with doing dense light curve measurements of asteroids for determining rotational light curves and potentially discovering satellites by that method. Most of the satellites have been discovered by this technique. He arranged for, well, he himself made some measurements and he arranged for someone at Nice Observatory to make measurements. And this is the combined light curve they got. You got a rotational variation over these bits and these deep drops here, an occultation and a transit. From that light curve, they were able to determine a period of 42.18 plus 2.2 hours, and the ratio of the size of the bodies, which was very close to the ratio of the size of these ellipses. So this was a case of one chord, one observer, 2 chords. The binary nature confirmed not by another occultation observation, but by a totally different technique. Now, this is a recent one from this year. Light curves at the left. Same drop there. Note that the light curve's going, comparison light curve's going that way, so is that. That's all the same light level. The light drop, that's 0 on there. The light drop is to the right level. It meets the 1.0 magnitude type limit. Then you come to look at the shape models. There's 2 shape models. I'm fitting this just to one shape model, and you can see you can position the long chord in 2 locations. One would be up there with the second chord out there. So you could possibly hypothesize that the shape model comes up over there, but it'd be a fairly extreme variation. Or you could push the chords down further and postulate that this end was something more of two bumps rather than that type of curve there. All a little bit indecisive. The key factor is on these shape models, there's that little bit there, which is hard to see, but there's a red line with an N on it. That's an indication on the shape models of the orientation of the axis of rotation. On most of the shape models displayed in occult, that it appears as a line at a clear angle, and it can be quite on the side. What that is telling us is that at the time of the occultation, the axis of rotation was pointing pretty close towards the observer, which means the asteroid was rotating in the plane of that image. Now, when you come to satellite systems of asteroids, the orbit of the asteroid will, the axis of the orbit of the orientation of the axis of the asteroid's orbit will more or less align with the axis of rotation of the asteroid. And frequently, they will be sort of locked into synchronous rotation. So the question there is, if you take this one, which is best indicates a satellite, we're looking at it as if face onto the orbit, given that. So that is separated from there. So it's going to do some sort of motion around there. Can you recognize a circular orbit, because the orbit will be circular, that goes around the body of the asteroid, which is plausible? And the answer is clearly no. I mean, it is, if the axis of rotation was differently oriented, the orbit could be going sort of side on a bit. But here, a circular orbit face on, with it being that close, is not physically viable. So conclusion out of this event is, whilst neither of these fit the shape model, which is a very poorly established shape model, there's no dedicated light curves behind it, that event was a grazing occultation, not a satellite detection. And the next two slides I don't have pretty pictures for, because they're still being finalised. This one was observed in January, I think it was. 3 observers. One observer got an occultation by one component. 2 observers got an occultation across the other component. All magnitude drops are greater than 1. The separation of the 2 components was far too large for elongate asteroid. But there's been some debate about what can or can't be extracted from the light curves from this event. And well, I'm not sure where this one's going to finish up, but it's a definite asteroid satellite. And this one, it's an intercontinental event. The occultation by the large component was observed in Europe, and of the small component, 2 observers in Japan. Separation of the bodies, well, orientation of the chords there excludes any sensible elongate asteroid. The main challenge with this is that the limiting magnitudes of the recordings barely get down to 1.0 magnitudes fainter than the target star. That's the greatest area of concern with this event. Now, out of all this, there's some interesting figures you can put together associated with what we've actually discovered in practice. There's the six events there. The diameter of the primary body is at the small end of things. We're looking at sort of 20 kilometers or less, more or less diameters. The satellite diameters, a lot of them are small, some are fairly significant. Their separation works out as being less than about 4 times the diameter of the main body, which means, I guess, my thoughts here is that gives you some sort of indication of how far away from the main body you might expect to find a satellite. So do you look for an event, monitor an event that goes over Sydney with a path width of 20 kilometres? Is it sensible to monitor that event in Sydney, in Melbourne or Brisbane and hope of detecting a satellite while you're wasting your time? It's that type of consideration. And that's it. Happy to take questions.
We're pretty pushed for time here. Yeah, okay. We'll drop the questions off till later. I'm assuming, Bill, are you still out there?
Yes, I'm here.
Okay. Can't quite work out in my head what time of the day it is at your place, but